All right, so this section is also a precursor, which you guys will be doing far more in detail in next class as well, section 8.2. So areas of a surface revolution. Okay. So what this ends up being is that what it means by area of a surface area, basically we're just figuring out the surface area as you rotate a function throughout, either the x or the y-axis itself. Okay. So let me just give you an example of what I mean by the surface area. So think of a can of soda, right? Right, here's your can of soda. We want to find the surface area. So how much area, what's the length of all the way around? So if I just cut this in half and just peel it all off, I essentially get something like this. Okay, so we want to figure out what is that area. That's why it's called surface area. It's just the area around it, the object itself. Okay, and you can think of anything, right? You can, surface area of a triangle, of shapes, a cube, things like that. And that's what we're going to be dealing with in this coming. It's just what's the surface area of this portions. Okay. And as we revolve around either the x or the y-axis itself. So either we're going to rotate it on the x, so like this way, right, this way here, or rotating around the y, so just going the other way. Okay. Now the good thing is this section actually follows up from the last one of finding arc length, because believe it or not, find the surface area is associated with finding the arc length, because we want to find the length. Remember, because if this is just a rectangle, area of a rectangle is just equal to length times width. Well, what is this portion? Well, that's the length or the arc length from one point to the other point. So that's what you kind of figure out when it comes to it. And then everything else goes from the situation of a cylinder, right? So when it comes to it. So when it comes to surface area of a cylinder, because that's essentially kind of what we're going to be dealing with a lot of it, the cross-sectional areas are going to be cylinders. The surface area around, if you rotate around the x-axis, is going to be 2 pi integral from a to b of f of x times, believe it or not, the arc length. So more practice with arc length itself, right? Kind of makes sense, right? Length times width. The length going up here, the width is up here, so the point is the function, and then the arc length from there to there. Right? And if you rotate it on the y-axis, same process, but we just integrate with respect to y instead. Oh, G. And there we go. So lots of practice when it comes to it. This one's going to be a little interesting how these integrals come into play. Just like the last one, the most of the work is just the setup of the problem. The integration won't be too much of the difficulty. Is again just the setting up is going to be a pain itself. Okay, so let's try this out so you can see how this will work out. So find the surface area obtained by rotating the curve. Y equals the square root of 5 minus x about the x-axis. So essentially we have this, right? And so therefore, before we do anything, we follow this. Arc length just takes the derivative. So y prime is going to be the derivative of the inside, which is just -1, times the derivative of the outside, which is now times 1/2 5 minus x to the -1/2 power. Okay. All right, so now we just plug them in respectively. So surface area is equal to 2 pi integral from 3 to 5 of the original function. So I'll just leave it like this, times our arc length. Yeah, so this squared to be negative over 2 squared. And again, right, since it's arc length, some things do cancel, which is the best part. So notice when you put this in, those cancel away. This goes away. So we essentially have integral from 3 to 5 of 5 minus x to the 1/2 power. And on the inside, we have 1 plus 5 minus x to the -1 power over 4 in this case, right? Okay. Now this is where I'm going to come into play here. All right. I can actually bring this inside because they have the same inside the square roots, right? This is the square root, this is the square root. So I can, remember that portion, separating them. If I have a times b, the same thing as square root of a times square root of b. Well, we're just going backwards. We're just, putting them together. So when I do this, and if I distribute here and there, that's times this, and this times that. Notice they cancel away, and you just get plus 1/4. Crazy, huh? Okay. And then putting these together, right, because 1/4, you can add it to 5. So we'll just put those together itself. So this would be 21/4. So this is the square root of 21/4 minus x dx. And now we just take the integral, right? It's not too bad of an integral to deal with. Right, just in case, I'll quickly do this. Let u equal exactly on the inside. Therefore, du is going to be -1. So just pop a negative on the outside, make it positive, right, when it comes to it. And now we're going to integrate with respect to u. So this is going to be u to the 1/2 power du. And with a negative on the outside. Okay. So integral this gives you u to the 3/2. Evaluate this at 2 pi from 3 to 5. And then we just plug in back in what we started with, right? So this is going to be 2 pi integral of -2/3 of 21/4 minus x raised to the 3/2, evaluated at 3 and 5. Okay, and then we just plug them in, like normal, right, when it comes to it. So plug in 5, plug in 3, and see what we get out. So this one we want a calculator. So 21/4 is 5.24. So that minus 5, and then raised to the 2/3 power, and then times it by -2, divided by 3, times 2, gives us -0.167 pi, and then we plug in 3 into there. So 21/4 minus 3 raised to the 3 power. Okay. Times a -2 divided by 3 times 2. So negative makes a